Thank you. Hope everyone is sufficiently full and buzzed, and let's get on with the talk. So we're going back to Greenland, and in this case, we're going to talk about biogeochemistry in lakes. And I'm an ecosystem ecologist, so I use big words like biogeochemistry when I talk. But we're going to first give a little context. And we know from previous presentations today that the Arctic is going through some unprecedented changes, especially in terms of warming. And not only in the temperature change that's happened over the past decade, but also the length of the growing season. And this has potential impacts for not only lakes, but the terrestrial systems in which they lie. Concurrent with these massive changes in temperature we see a trend in the loss of sea ice. And this is a pattern that people have talked about today already. And 2 of the years where this has been a major issue has been 2007 and 2012, where we've seen these patterns of massive sea ice loss compared to previous years. Additionally, we have increases in primary production in the North Atlantic and Arctic Oceans, concurrent with these losses of sea ice. And again, I'm an ecosystem ecologist, so I'm not only interested in how these large-scale patterns are affecting the systems I'm looking at, but I'm also interested in local controls on those systems. So if we look at a lake in Greenland, realize that there are changes that are going on in the lake, and Jasmine talked about a few of those changes that may or may not be related to temperature changes, but also the whole terrestrial environment is also a major control on the patterns that exist within lakes and different features I'm going to talk about today. So if we zoom back out again and we look and we think about the temperature changes, we think about sea ice persistence, we think about primary production, another thing that's very predominant over the Arctic is the existence of mass amounts of methane. And as we know, methane is a key greenhouse gas, and it has major climate forcing potential. And over the same time period that the other 2 figures were alluding to, you can see massive amounts of methane being released from the Arctic. And they're coming mostly from the terrestrial areas of the Arctic, the parts that are exposed. So what we wanted to do in Greenland was sort of get a feel for how much methane is actually important in the ecosystems around Greenland, to get a survey and compare it to some other areas that we know a little bit more about in terms of methane ebullition and the relationship between carbon, nitrogen, sulfur, and a lot of other biogeochemical cycles that interest us. So we're back in the southwest portion of Greenland here, and again, near the town of Kangerlussuaq. We're working in a series of lakes along a gradient moving from the ice sheet about 90 kilometers towards the coast. And there are 5 lake districts in which we have data. First of which is one that Rachel talked about earlier. It's a series of lakes inside of the Nunatak, which is actually emerging from the Greenland ice sheet. We have a series of lakes that are close to the ice sheet. And then as we move farther and farther away, we also have a gradient of warmth. Areas down here are generally warmer than areas up here. So we did a very simple data collection. We collected water not only for a suite of lake variables, but we collected gas samples from all lake depths across all of these lakes that we studied. And we were looking at some patterns to see if any exist across the landscape. We get some unexpected results. We got some unexpected results, sort of in sulfate, which is something we weren't necessarily looking for. What this is, it represents percent change in sulfate found in lake water over the past decade. So this is 2003 minus the data that we found from lake water samples in 2013. And you can see that across lakes, and these aren't in any particular order, but across lakes you can see a net increase in sulfate in lake water across the region. And this is an interesting pattern because, again, I was talking mostly about methane in my build up to this slide, because methane and sulfate have a relationship that's pretty consistent throughout the biogeochemical literature. And that relationship is generally thought to be a negative relationship. It's thought that sulfate can reduce the amount of methane that you would see inside of lakes or coming out of lakes. And there's two possible mechanisms for having this inverse relationship. The first of which is that sulfate-reducing microbes and methanogens are competing for the same resources. And those resources are acetate and free hydrogen ions. So this inverse relationship likely exists and has been seen throughout other lakes and in the literature because of this competitive effect. The second is that sulfate reducers can also oxidize methane. So there is a drawdown of methane because the sulfate reducers are actually using it in the process of methane oxidation. So these are two possible mechanisms that you would expect to see this negative this negative relationship, and has been seen consistently across the literature. So what I decided to do was see how this relationship holds up in our lakes. And it doesn't. So, but we'll talk through it. Negative data are still data. All right. First of all, I'll note that I'll point out that you can see basically no clear relationship. Well, you can't really draw a line through it either, so I'm not going to try. But there's no clear relationship between sulfur, and there's no clear relationship between methane and sulfur here. But I do want to point out and give it a little bit of context so you know some of the extremes that we're actually seeing in these data. First of all, I'll point out that this yellow box represents the typical range of sulfate that you would see in lakes in this region. And this is just doing a quick survey of Arctic lakes of this same ontogeny. Here, you see a typical range of methane that you would see in lakes of this area of this ontogeny. And what you'll see, if we first focus on the sulfate axis, you'll see that across all levels of sulfate, you're still getting typical amounts of methane. And you can see that in some cases, even when there's a small amount of sulfate, you're getting lots of methane. So not only are you getting a lot of methane that's outside of the bounds of what we would typically see in lakes of this type of this region, you're seeing a lot of sulfate in levels that you would typically not expect to see in lakes such as this. So we're sort of seeing atypical results, which to me are actually a little more interesting than seeing that relationship that I was hypothesizing earlier. So why could we be getting a lot of sulfur or a lot of methane? So here are some thoughts. First, we don't think that the sulfate is necessarily coming from sea salt deposition, because we would expect to see a concomitant relationship or a concomitant change in chloride along with the sulfate, and there's actually no relationship if you look at some of the correlative data that we have. There's no relationship between sulfate and chloride. So we're hypothesizing that it could actually be coming from biogenic sources. So if you remember in my first few slides, I was talking about the increases in primary production in the Arctic, in the warming surface waters and lack of sea ice. So the enhancement of primary production in the oceans is actually stimulating these phytoplankton to release sulfur-based compounds into the atmosphere that are then broken down and can actually be transported to continents. But for methane, what are some possible mechanisms? First of all, we have some indications that DOC input is changing not only the amount but also the quality, which could have a role in reducing the competition between the types of microbial groups we're focusing on. Second, a changing active layer. We know that the active layer is increasing. We know we're getting permafrost melt, and there's new evidence to suggest that methane is being held in the permafrost, and as it melts, it's going into the lakes, which is contributing to lake budgets of methane. And thirdly, there's a new paper that came out a few weeks ago that has linked water column production to primary production in the water column, which in the past has been sort of ignored and thought it never happens because you have a lot of oxygen in the water column. But we think that this paradigm is changing based on these data. There's still a lot of work to do. Thank you for listening. I'll shut up. Yes, ma'am.
Is it possible you could have any kind of volcanic sulfates in the water?
It's possible, but the evidence from the other parts of the Arctic, the Canadian Arctic, using isotopic data suggests that most of it is biogenic. We don't have the isotopic data, but if we did, I think we could tease apart if it's volcanic versus biogenic, but the trends are indicating it's likely more biogenic. Thank you.
Thanks, Robert. All right, so now we have Chris. Sorry. We now have Chris Lack-Alexis with Maritime Adaptation and Cultural Boundaries of Frenchman Bay, Maine.
Good evening, everybody. I'm Chris. I'm a first-year master's student at CCI, and I'm going to give you a brief introduction and overview of some of my past and current research concerning maritime adaptation and cultural boundaries in Frenchman Bay, Maine. There are approximately 2,000 documented shell midden sites in the Gulf of Maine. Shell middens provide an evidence of coastal settlement patterns, maritime adaptation, and artifact styles that reflect a distinct identity in Maine's prehistoric Native Americans. Shell middens in and around Frenchman Bay have produced an unusual number and variety of bone tools, making the area very distinct. Although bone tools have been documented since the first excavations in the 1920s, it still remains unclear as to whether these tool forms represent a localized maritime adaptation or an identifiable cultural region where bone was the preferred method for tool production. Localized complex cultural patterns appear in Frenchman Bay as an adaptive strategies were developed to exploit the rich marine resources located within the local environments. These adaptive strategies can be attributed to a combination of technological changes, social organization, where different cultures found different solutions to common problems. It is evident that both marine and terrestrial food resources were utilized throughout the year, and based upon the variety of faunal remains found within the middens, seasonality can be determined. Cultural differences are interpreted from the visible material patterns that significantly differ in content and meaning. Due to visible and distinctive traits, projectile points and pottery are commonly used to identify cultural boundaries. But cultural identity is expressed in many other different ways, including other forms of technology and ritual artifacts. We need to analyze the various artifact forms that represent distinct cultural practices in order to determine if cultural boundaries are identifiable. As an example of a distinct cultural boundary, we look at the Kennebec River, where north and east of the river, side and corner notch points are most common within the shell middens. And then south and west of the Kennebec River, you're finding the Levonic triangles in the middens over the side and corner notch points. As noted earlier, the most common projectile points in the east and central region of Gulf of Maine are the side and corner notch points. And they appear great numbers compared to other projectile point styles found in the middens. Another tool form that's abundant in shell middens in Frenchman Bay is the uniface scraper. And these are most commonly found in assemblages with corner and side notch points. And both of these artifact types are made from a wide variety of sources, from local materials to exotic materials that are acquired through long distance trade. Bone tools are the most diverse artifact found in the Gulf of Maine. These tool forms are abundant within Frenchman Bay and then just to the west into Blue Hill Bay as well. Due to the high variability of bone tool forms, there appears to be an increased specialized dependence upon bone as the preferred source material for exploiting maritime food resources. The simple bone point seen in the bottom of the slide here is the most visible bone artifact found within shell middens in Frenchman Bay. There's very little understanding as to why these are so abundant and what they were used for. They've long been speculated as projectile points, spear point tips, or even fishing lures. The 9 shell midden sites in this graph range from Martha's Vineyard to Passamaquoddy Bay. They've been chosen as the major sites in each of the larger bays within the Gulf of Maine that represent the late ceramic periods. I've chosen to compare only the bone points seen in purple against the stone tool forms found in these middens due to the high density of just this particular artifact type. All other forms of bone tools have been omitted. They just haven't been taken into account. As you can see, the bone points appear to be the most abundant tool form within Frenchman Bay and into Blue Hill Bay compared to the rest of the Gulf of Maine. While comparing frequencies among these selected sites, we have to carefully examine the sample sizes that were collected, as well as the proportions of each tool form within each site. Jones Cove is a late woodland period shell midden and is the primary focus of my research. In 1928, it was one of the first shell midden sites to be excavated in Frenchman Bay by the Abbey Museum, under the direction of museum curator Walter D. Smith and supervised by Warren K. Moorhead of the R.S. Peabody Museum at Phillips Academy. In 2006, under the supervision of Brian Robinson, the University of Maine Department of Anthropology conducted a MAPI-funded field school that I had definitely had the privilege to participate in. And as you can see us, that's our field school on the bottom there. This is the site map that was created in 2006 by the University of Maine, showing the units of excavation that our field crew conducted. The red area indicates the estimated extent of the 1928 excavations, as there was no formal map created at that time. Moorhead implemented rudimentary excavation techniques as they took just a little over a week to excavate the midden using garden tools and clam rakes, forming a sheer walled trench while shoveling the dirt behind them without screening any soils. They moved from the shoreline inland, and in the process, they encountered many features and collected many artifacts, but none of these features were documented. They were just noted briefly. The blue areas indicate undisturbed portions of the shell midden, where in 2006, we unearthed some very, very interesting artifacts, features, faunal assemblages. And I had the awesome time of excavating the upper trench with Sam Haynes. He was one of our field crew as well at the time. Although Moorhead excavated most of the midden, they left behind a lot of materials that we collected, including the faunal remains, which are very important in determining the seasonality of this site. My research within Frenchman Bay, more specifically Jones Cove, contains 2 components. First, in-depth analysis of bone and stone technology and faunal remains will be conducted to determine if there was a correlation between tool types and specialized resources, or if the tool proportions as a whole could represent a distinct cultural practice in comparison to the other late woodland sites within the Gulf of Maine. Secondly, DNA analysis of select bone tools will be conducted to determine if a certain species of animal was specifically chosen for bone tool production. What we're looking at in specifics is the simple bone points. To determine if this is a form of hunting or fishing ritual within the Gulf of Maine, as it has been previously documented among hunter-gatherer groups here in the north and east regions of the United States, North America. For example, with the Montanai, the Naskapi, and the Cree, that special preparations and specific rituals were conducted around certain animals prior to and during the hunt, as well as when the animal was being procured for consumption. According to some Native American ideology, these ceremonies and rituals were performed in order to avoid offending the spirit of the animal that they were hunting and eating. Continued research and analysis of main shell middens is necessary as these archaeological resources are continuously being threatened by sea level rise and erosional factors. There's still many unanswered questions when discussing shell middens and the cultures that created them. While continued analysis of late woodland shell middens and their assemblages, we can develop a better understanding of culture areas and the adaptive strategies that Native Americans within the Gulf of Maine. Thank you. Yes.
I didn't have a good feeling for scale. Those bone awls, were those natural joints or were they carved with the knobs on the top?
The tip ends were definitely stripped down, yeah, to make the fine points.
But the blunt end, is that a natural joint?
Yes.
And how long were they?
They could range anywhere from just a couple of inches up to maybe a half a foot, depending on which species of animal was utilized for those. Any others? Oh, there's a bunch. I knew as soon as I started walking away, the questions pop out of the sky.
Are you going to be doing fauna analysis at the Abbey, or are you going to be bringing it back and using our comparative collection?
Maybe a little both. I know most of it will be done at the Abbey. I'm not sure if there are rules and regulations for leaving site with our.
I want to see it.
But I will be, we'll be doing a comparative analysis with what we collected as well. I do believe, I think our sample is slightly larger than theirs. Yes.
I was just wondering about the kind of unidentified purpose bone points. How big are they, and what's your best guess as to what they?
With the simple bone points?
Yeah.
I've seen a couple of theories on them, and I'm tending towards they may be a central prong type with a Leister point for use for spear fishing, to where you have two Leister points that come out, and then you have a center prong in the middle. So when you stab the fish gets trapped in the Leister points themselves and can't get away.
Okay, so they're pretty big.
So, well, they range just from a couple of inches to, and then they get large. Some of them, but the larger ones are more highly decorated than the smaller ones, and those are considered prongs and not simple bone points. Thank you.
Thanks, Chris. All right, next up we have Elena Korotke, developing an ultra-high resolution record of the last glacial interglacial transition from the Rice Ice Core in Roosevelt Island. And I do apologize about the last name.
Hi, it's very good actually.
Oh.
Yeah, so my name is Elena. I'll be talking today about kind of new research we start to do. We try to develop high resolution record of the transition from last glacial to interglacial period using the ice core section from a Rice ice core. And just a little information about Rice ice core. Rice, the Roosevelt Island Climate Evolution Project, is an international partnership between several countries. It's led by New Zealand and involves the United States and some other countries. The main goal for this project is to understand the stability of the Ross ice shelf in the past and predict how it will behave in the future. The ice core were drilled during 2 field seasons, from 2011 to 2013 to bedrock. It's 764 meters deep. And we have a section from a deep part of the core available for analysis here in New Maine. So we started to analyze this ice core using laser ablation ICP-MS, which was Skylar was talking about just some time ago. And this is the picture of this system. Advantage of using laser ablation ICP-MS because we can get super high resolution. This core were actually being processed using continuous melter system, but the resolution is about 1 centimeter. We can get resolution about 120 micrometers, which is very, very high resolution. And we analyze 3 elements: sodium, calcium, and iron. Sodium is we're interested in sodium because it's mostly come from marine source, and it represents the marine input to the ice core side. Calcium is a combination of dust and marine sources, and iron is mostly comes from crustal dust source, and it represents the dust input to the Roosevelt Island. We did some preliminary work on this rice core. This is a different section. It's from 493 meters depth. We wanted to see if actually laser work will show us any good results. And this plot shows the iron record. It's the intensity of iron. And we found out that iron has a very distinguished peaks, which we believe represent annual layers. And so this is the 16 centimeters of ice core. We have 4 major peaks. So based on these iron peaks, we can assume that annual layer thickness of this part of the core is about 4 centimeters per year. And then we compared it from annual layer thickness calculated using preliminary time scale. This time scale was developed based on isotope match to base divide, and it has a very large dating uncertainties. But nevertheless, our annual layer thickness is very close to this depth H model, which is very good. So this plot shows on top is the isotope record from the rice ice core. It's a 10 centimeter resolution against depth. The green box represented ice core section what available for laser analysis. And this plot shows the kind of zoom in version. So again, the green box, this ice what we have now in UMaine. So it's like from 672 from up to 686 meters, and another deep section from 692 to 700. Why we decided to analyze this section? It's because it covers the transition from last glacial to interglacial period. So it's very interesting part of the record, and we hope to develop very high resolution data so we can see how fast the climate change occurred during the transition. So we plan to analyze all ice what we have. So far, we analyzed 2 sections, one in the deeper part, right at the beginning of the transition, and another part during Antarctic cold traversal. But starting to work on this ice, we have some problems. This is the actual pictures of the ice what we have, and you can see some pieces of ice that very nice shape, but some of the ice is really, really bad. It has a lot of cracks, especially on the bottom, it's so many cracks. And to analyze it on the laser, the piece of ice needs to be at least 4.5 or 5 centimeters long. So if we have this type of ice in here, it's not possible to analyze on the laser. And sometimes even when I have nice looking piece of ice, but it could be some tiny crack in it, and it's not possible to seal, so we can't use it on the laser. So this 2 sections what we start to analyze, the green box represent, and after encountering a lot of cracks, this actually what we were able to analyze. So green box shows what we're able to get a laser data, and white just all the gaps. So it's very unfortunate we can't get the continuous records, but it's still, I think we still can have interesting data. So far, this is just the first laser data we have. Again, so this is the so this is the part, it's right here, and the deeper part, beginning of the transition, is right here. So sodium in the blue line, calcium green, and iron is red. And we can see a lot of interesting variability and very high resolution data. And when I first look on this data, I kind of thought it's very interesting that the mean level, like from this piece, when it's much colder, the concentrations are much lower of all elements, the sodium, calcium, and iron. And when temperature, like deuterium, is more positive, so it means it's warmer temperatures, the concentrations are higher, which kind of unusual compared to other ice cores, but it could be, I believe, explained because the Roosevelt Island located right on the edge of a Ross Ice shelf, so when it's during warmer temperatures, the open water source was much closer to the site, so that's why we have more sodium. And maybe because during the warmer temperatures, some local coastal areas in Antarctica became ice-free, and that's why we start to have more dust. And another major point, we wanted to see if we still can see annual layers in this deep part of the section. And this tree plot shows just the example of the iron intensities. And we believe each peaks in iron represent different years. And I tried to calculate how many years we have in those three sections. And this is in red, like 0.39 centimeters per year. And again, we compared it to this annual layer thickness from this depth H model what we have now. And the values are very similar, which is good. It means we can confirm that this depth H model is correct. And just a couple of examples what we have now, we can see some interesting transition. For example, this plot covers about 18 years. And we can see period of high dust loading, it kind of starts and ends very abruptly. And another plot shows period of about 80 to 90 years. And we can see, for example, big shift in the sodium when the concentration increased and also changed to different frequency. We started to have much more storms. So this is all what I want to show so far. We're going to continue to laser all the pieces what we can. And I hope we can get some interesting data soon. I can show you. Thank you.
I didn't understand your age model. It sounded as though it was from the waste divide, but this is this a model that then can be somehow numerically applied to the rice?
They used, I think for this period of time, they used 4 isotope matches from rice to waste divide and try to interpolate between those isotope matches. So it's not ideal, but that's what they have so far. They're still working on it.
Mm-hmm.
Thanks, Lena. Okay, so next up is Benjamin Partam. Test using UAV gathered imagery to measure superglacial lake depths.
Well, the title of the talk has changed slightly. It's now determining superglacial stream symmetry, not lakes. The methods are somewhat similar, but the reasons for doing it are different. And how do I change slides? This thing? Yeah. Okay. So my name is Ben Partam. I'm a first-year grad student here. So the ultimate goal of this project is to better understand how meltwater is on the top of glaciers. So I'm looking at superglacier streams, and superglacial streams are on the top of glaciers. And so I'm developing a remote sensing technique for finding the bathymetry of streams that is done cheaply and efficiently. And the major driver for that is that satellites can't resolve small streams. They could maybe resolve a big river. Lakes up there have been looked at for a while, and you can get lakes from satellite imagery. However, a multispectral satellite image, this entire room is 1 pixel. And for my UAV, my unmanned aerial vehicle, a UAV, flying at about 100 meters, this is 250,000 pixels. So there's a big difference. The objective is to assemble a UAV with an integrated camera, autopilot, and GPS, fly it over, collect visible wavelength imagery, use the imagery to find stream bathymetry, and then compare the bathymetry to ground truth measurements. So where is superglacial meltwater? As I said, it's on top of the glacier. Here are pictures of Greenland. You can see lakes forming, and then there are streams that go in between them. That's more like a river than a stream. And they happen during the summer. So in this graph, it shows the amount of water in this area of Greenland, also near Kanger. And at the beginning of summer, there's no water. Middle of summer, there's a lot of water. End of summer, there's basically no water again. So the question is, where does the water go? So the water goes into lakes, and then it feeds into streams when it overflows and goes into more lakes. And eventually, it either leaves the glacier off the top, or it goes into the bottom, or it goes inside the glacier via a moulin or a crevasse or some other entry point. And from there, it makes its way down to the bed. And why is it interesting that the water goes to the bed? Because that affects glacial flow rates. And the more water you have on the bed, it's been shown that the faster the glacier will move. And it's sort of like, in a drastic oversimplification, if you're driving your car in the rain and you start to hydroplane, you've lost traction with the ground. And that's what happens when a thin layer of water gets under a glacier, is it loses the friction that holds it in place, and it starts to move faster. And since they're already going downhill, they speed up. And the other thing is that it loses mass. So when the snow or ice melts and becomes water and leaves the system, you get a reduction in mass. And you want to know what the mass balance of a glacier is to know whether it's retreating or advancing. Generally, they advance when they get bigger, and they retreat when they get smaller. So that's why you want to look at mass balance. So why do we care about superglacial streams in this instance? It's because when you look at them, you can figure out how much water, help figure out how much water is on it and how much will discharge. Whoops, that's not the one. So these are pictures of Greenland in the last few years, and it's measuring how many more melt days there are than in the 30-year period from 1980 to 2010. And in 2012, this is 2012 in Greenland, red represents 30 days above the average number. So there was a lot of melt over almost the entire country of Greenland. So when you have atmospheric warming, you can get increased meltwater, and with increased meltwater, you get increased number of streams, and you also get increased freshwater discharge into the ocean. And Greenland could contribute roughly 6 meters to global sea level change if it all disappeared. And finally, well, not quite finally on this slide, but Alaska glaciers have contributed on the period from the mid-1990s until about 2000, twice as much to global sea level rise as Greenland did. And this changes the salinity. And ocean currents and other things are driven partly by salinity. So if you disrupted the North Atlantic circulation, such as the Gulf Stream, it would be a global impact, and it would change everything. So how am I going to find this stream bathymetry? I have a quadcopter similar to this. I'm going to mount a camera on it. And this is a picture of a lake. It's not a stream because satellites don't resolve streams, so I couldn't get any satellite imagery of streams. But you program something into the autopilot flies it for you, it takes pictures while it's over it, and then you have pictures to study. Why would you use a UAV as opposed to, say, a helicopter or an airplane? It's because they're much, much cheaper. my UAV costs less than 1 hour of helicopter time. And it's portable. I have it when and where I want it. A helicopter, you have to rent it. Sometimes other people want to rent it, then you don't get it. Same thing with airplanes. And I also get high resolution imagery. As I said, this room is 1 pixel from a satellite in the multispectral sensor, whereas I have 250,000. So with these pictures, I'm going to use radiative transfer. That's been used often in lakes. And then I'll also ground truth it using rulers and such. So how do you use radiative transfer to get depth? So the sun's here, and you have your sensor here. The sensor can be on a satellite or it can be on a UAV. The sun puts out light, it goes down through the atmosphere, it scatters in the atmosphere, and some of that scattering hits your sensor. And then in this case, it hits water, and it hits the surface, and it bounces off the surface and goes to your sensor. Then some of it gets through and goes into the water column, scatters, hits your sensor. And finally, we get to what is really interesting is the bottom. So it reflects off the bottom and goes up and hits the sensor. And from that, you can isolate the bottom and use it to solve depth. So the process would be, I take my UAV, I fly it over, I can fly it over a lake too or a stream. And then I separate out and compare the intensity of light here to the intensity of light along the edge. And that will give you, if you take this equation and manipulate it with some math and stuff, from that you can isolate the depth. And from the intensity, you can calculate the depth. And then I'll compare those depth measurements that I get derived from the remote sensing with ones that I get while sitting in a boat and hopefully doing something more advanced and dropping a string with this weight. And I have tape measures and such. And from that, I'll create a map of the stream. Compare the two and see what I get. So the expected outcomes is that my project will yield a method to remotely sense the bathymetry of superglacial streams. And the advantage of doing this is, number one, satellites can't do it. The second is that if you're doing it by hand, like in ground truthing method, you can only do as far as you can walk in a day, which maybe isn't that far if you're taking measurements. And it's also, whoops, it's lower cost than a helicopter and airplane, and I get much better resolution than from satellite imagery. So the future work, when this method works, is to quantify the amount of meltwater that's on top of a glacier and to better understand the glacier dynamics that meltwater plays a role in, as well as ocean freshening or the changes in salinity, which impact ocean circulation, local and global climate, and ecosystems, especially fisheries, and fisheries are fairly important in Maine. So that's what will be done in the future. And finally, I'd like to thank these people for giving me a lot of help on my project. And are there any questions?
When you're able to do this in lakes at some point, is there a depth beyond which you think this is not going to be
So
useful?
it's about 3.5% per meter of attenuation for sort of your average wavelength. Different wavelengths go to different depths. One of the ways that you can correct for all the scatter is you look at optically deep water, and that's generally considered, I think, about 40 meters deep. So you're not going to get much bottom reflection at about 40 meters. But you know, red gets extinct really quickly, and then blue and green go further. So.
With streams, I'm wondering, since it's moving water, are they carrying any kind of rock flour in them or anything that's going to cause issues? And that's question one. Yep. And then number two is thinking about how much water, how are you accounting for discharge?
So I'm not actually trying to measure the amount of discharge initially. I'm just trying to measure the bathymetry so you can calculate a volume in a certain area, not necessarily how much goes through it. If I wanted to measure how much goes through it, I'd put a stream gauge in, or I'd use dyes. And now I forgot your first question.
Oh, just wondering if like, is the stream, since it's moving, is it picking up stuff?
So the stuff that comes out at the bottom of the glacier is heavily laden with rock flour and whatever else is under there. The stuff on the top, especially in a place like Greenland where it's a big ice sheet and everything's up high and there's less dust, it'll be quite clean. Where I'm doing it in Alaska, it'll also be pretty clean because it's on the top, so there's no real erosion of rocks and stuff on the top.
Your superglacial streams won't have sediment in them, but they may have air bubbles and they may have ice crystals.
Yep. So that's why I do a ground truth, is to see, maybe there's a correction factor that you can use or something like that. Okay, thank you.
Thanks, Ben. Okay, our last speaker for the day is Nora Theodore. She'll be talking about recent trends in Jordan Pond, the impact of changing clarity and epilimnion thickness on phytoplankton community dynamics.
Thanks, Rain. Thanks for sticking with me, guys. I know it's been a really long day, so I'm the last one, so we have to leave after this. But my name is Nora Theodore, and I am a master's student of Jazz and Sorrows. So I want to begin here. My research is part of a larger body of emerging research that's using lakes as sentinels of environmental change. So a sentinel meaning an early warning signal of larger changes that are predicted to occur. One sentinel response that I'm particularly interested in exploring is transparency. So transparency is a really great sentinel response due to the fact that it reflects changes that are occurring in the broader watershed system. So it's integrating those changes. So one such sentinel is Jordan Pond in Acadia National Park that many of you may be familiar with. So Jordan Pond is the clearest lake in Maine. And we want to use Jordan as a sentinel due to the fact that it is so clear and will reflect changes in water clarity that we are predicting. So this has global importance because it can be used to see what will be occurring in other lakes in similar regions. But it also has local importance. So we know Jordan has lots of economic value to the state. It brings in lots of tourists, but it also has aesthetic value, and it's also a drinking water source. So Jordan Pond is very important for many, many reasons. So this is sort of the focal point of my research, or the jumping off point. So thinking about clarity in Jordan Pond and Acadia, this is a suite of 6 Acadia lakes that we've been looking at, and it's measuring Secchi depth, which uses a Secchi disk to measure lake clarity. And what we see here is that transparency and clarity has been changing in the suite of Acadia lakes. And in recent years, more specifically, transparency has been declining. And those trends are particularly pronounced in Jordan Pond, which you see there in the upper left. So this is further reasoning why we want to use Jordan Pond as a sentinel, or we can use Jordan Pond as a sentinel because of the pronounced changes that we see occurring there. Another thing I just want to point out while we have this figure up is that we have a really nice long-term data set that comes out of Acadia, as I think Kate mentioned earlier this morning. So that's something that is exciting as I move forward in my research, that we have that long-term record to use. So what are the main drivers of lake clarity? Well, previous studies have sort of brought these, they did say that chlorophyll, so algae, and dissolved organic carbon, or sometimes called dissolved organic matter, are the 2 main drivers of lake clarity. So looking at those 2 drivers in the same suite of 6 Acadia lakes, both dissolved organic carbon concentration and chlorophyll concentration, again, same set of lakes. We're looking at the black points being dissolved organic carbon and the open points being chlorophyll. We see in 4 out of the 6 lakes significant increasing trends in DOC, while we're not seeing any significant trends in chlorophyll concentration. So this would suggest that dissolved organic carbon is a more important driver of lake clarity in these Acadia lakes than chlorophyll. So what are the drivers of these increases in dissolved organic carbon concentration? One of the theories that we're looking at is actually reduction in wet sulfate deposition that we've seen as a direct result of the Clean Air Act Amendment of 1990. So this is really exciting, right? Because it's an example of a successful piece of environmental legislation, which we always like to hear about. And the hypothesis with this is that with reduced acid deposition, that also reduces the ionic strength of soils, and that results in an increase in organic matter solubility. So an influx of that dissolved organic carbon into lakes such as Jordan Pond and Acadia and across Acadia. And this influx that we see as a result of reduced acid deposition can also be exacerbated by changes in precipitation events that we have seen from figures such as this that's come out from the Maine Climate Future Update just this year, and also looking familiar from Kate's presentation this morning. But just to reiterate the point that we are expecting increase in magnitude and frequency of precipitation events. So this could exacerbate or have an additive effect on what sulfate is already doing to the dissolved organic carbon availability in soils. So I'm really interested in how changes in clarity will be influencing the thermal structure of lakes, specifically through epilimnion thickness. So Jasmine talked about thermal structure a bit in her talk as well, but just to review, we have the warm water epilimnion layer, and then we have that rapid change in temperature that we see in the thermocline, and then we see a cold water hypolimnion. And you can see that same trend in this figure here, where we have the epilimnion and then the thermocline, and then moving down into the hypolimnion. So I'm interested in epilimnion thickness because it's predicted to change with this change in clarity and dissolved organic carbon. So the two main drivers of epilimnion thickness are DOC through its influence with light attenuation, as well as wind. So just to get at that point here, we see that with, well, I guess starting here, this is sort of a system similar to how Jordan may be, where there's penetration of light quite deep into the lake, and that results in a thicker epilimnion. So with less DOC, we have higher light penetration and a thicker epilimnion. Whereas we see if there's a shallowing of light attenuation, which we expect to happen with increases in dissolved organic carbon, we would see a thinning of the epilimnion, the thickness, thinning of the thickness. Okay? And I don't think I mentioned it, but the other important driver is wind. Did I mention? I did, yeah. Okay, so wind is important. It depends often on lake size, which I won't really get into now, but I will be in my research looking at sort of how wind is influencing thermal structure as well, specifically epilimnion thickness. So for my research, I am still in the early stages, but I will be addressing three main questions. First, how is epilimnion thickness in Acadia and specifically Jordan changing? How do we predict these changes? What do we predict to occur also in the future? What are the drivers of these changes? So what is DOC or wind, which is more important, are both important? We will see. And also, most importantly, what does this mean for the productivity in the lake? What does this mean for phytoplankton community dynamics in these systems? So in terms of what I'm predicting to see with phytoplankton, with a thinner epilimnion, we actually expect that there would be more light exposure for those species that are confined to the warmer waters, and therefore we would have a higher rates of primary productivity in the lake. So this is really interesting to see too, maybe to apply on a broader scale. How will the phytoplankton dynamics and productivity in lakes change with this changing clarity? So how will I address these questions? We have a really awesome buoy in Jordan Pond. I hope you all get a chance to see it at some point. It's been deployed for the past 2 field seasons. We're really hoping that the ice gets off that lake so we can get it in as soon as possible, hopefully mid-May. And here's the schematic of the simplified schematic of the buoy here. This XO2 multi-parameter sonde is sort of the data logging center of the buoy. We have 2 photosynthetically active radiation sensors as well. And so we can measure light attenuation and see how clarity is changing. And it's so nice to be able to do, have this over such a high frequency data. Okay, anyway, temperature also, I'm getting off my here. Okay, so we also have a temperature string, so we can see how thermal stratification is changing as well. So, and this is sort of what I was getting at. It's amazing because this data comes right to my desk from the buoy twice a day, but we're logging data every 15 minutes. So as opposed to having these two, discrete sampling points, we have continuous temperature data over the course of the field season. So we can really understand more what's happening in the in more fine scale detail. So this is just the suite of water quality characteristics that the buoy is measuring. And also to say that we have a Jordan or a weather station that's mounted on Jordan Pond House that we can pair with the buoy, which is also great. And sorry, I forgot to mention to say too, I'm trying to go back, but it won't let me, that it's really nice to have this high frequency data that we can pair with this long-term record that we have in Acadia. Oh, and now it's going back. So, and the other thing to mention is, I'm clamming up here, but we have a public education and outreach component of this project. So we're going to be putting a kiosk in the Jordan Pond House this summer so that the public can interact with the project and understand what's going on. So with that, I will end.
You said that the clarity of the ponds in Acadia was decreasing, but all of those graphs had curves fitted to them, and the data kind of had this U shape that would imply the clarity is increasing again. Just wondering if you
So
could
it's actually,
speak to that.
it's increasing, clarity is going up is decreasing.
Okay.
So it's possible that it's recovering. So with this, there was maybe this increase in acid deposition that caused the clearing.
Okay.
So that it could be, in fact, rebounding to a prior state, possibly. Thanks, guys.
All right, we'll see everyone in the morning.
6:30.